discussed.
Recording in progress.
The program includes 4 talks, each focused on a particular broad area of research where the work of Weinberg led the breakthrough progress. The speakers of the day do not need any introductions since they are very well-known eminent scientists, and I'd really like to thank them for accepting to give a talk for this Weinberg celebration. And also, I'd like to thank the GGI Breaks organizers with whom I'm sharing every effort to make this day a great day, especially for the youngest generation of physicists. And the impact people are still connecting on Zoom. We are quite a number. Stephen Weinberg was a giant, as I told you. For those who were not able to attend, the event is live streamed, and you can find in the chat the link for the live streaming for generations of physicists, and it is at the heart. All the infos are in the chat, yes, and the videos of the talk will be uploaded on the GGI webpage in the next days. Quantum field theory and cosmology still form the foundation of our understanding of physical reality. I must confess that I did not know how wide was the area of the research covered by Stephen Weinberg, and the number of topics where he contributed in a seminal way. Of course, everyone knows that he won the Nobel Prize in 1979, which is shared with Lesho and Abdul Salam, for his work unifying 2 of the nature's fundamental forces. In fact, he realized that by applying the Peter Higgs mechanism to the weak force, he could describe in a unified way the electromagnetic and weak interactions. And this became a foundation for the current standard model of particle forces. But Weinberg's research touched on many other areas. It's amazing the list of important results that carry the Weinberg name. Just to remind some of them, the Weinberg sum rules, the Weinberg operator, the Weinberg angle, the Weinberg-Witten theorem, the Lee-Weinberg bound, the Weinberg soft graviton theorem. And in addition, there are his groundbreaking contributions which do not carry his name, including the development of the effective field theories and cosmology. This event was to be a celebration. Do you hear me? Maybe they are calling for some problem. I hope you hear me. This event wants to be a celebration of Stephen Weinberg. His contribution will be put into historical context, and its relevance for present-day research will be discussed. The program includes 4 talks, each focused on a particular broad area of research where the work of Weinberg led the breakthrough progress. The speakers of the day do not need any introductions since they are very well-known eminent scientists, and I'd really like to thank them for accepting to give a talk for this Weinberg celebration. And also, I'd like to thank the GGI Breaks organizers with whom I'm sharing every effort to make this day a great day, especially for the youngest generation of physicists. People are still connecting on Zoom. We are quite a number, and as I told you, for those who were not able to attend, the event is live streamed, and you can find in the chat the link for the live streaming. All the infos are in the chat, yes, and the videos of the talk will be uploaded on the GGI webpage in the next days. Some details about the organization. We have 2 sessions of 2 talks each, divided by 20 minutes of break. At the end of each talk, there will be a Q&A session and an overall free discussion at the very end of the day. Roberto Contino and Enrico Trincherini will coordinate the Q&A sessions, and I want to thank them for doing this job. So please write your question in the chat. That's all from my side, and I invite Roberto to open the session and to make to clarify other points that maybe I forget to do. Thank you again, and Roberto, please.
So thank you, Stefania. I think you clarified most of the things. As you say, I mean, the presentation of the speakers will be very, very, very short. Concerning how how the event will evolve, I think we can devote the 10 minutes after each talk to the more specific questions on each talk, and then reserve the more general questions and comments to the final discussion session. So the first speaker is Riccardo Barbieri. So Riccardo is professor at Scuola Normale Superiore in Pisa. He is certainly an expert of the standard model, which is the topic of his talk. The title is The Standard Model of Particle Physics. He made very important contributions, in particular regarding precision tests of the standard model, where he's an expert. He is also very well known for his work on naturalness of the standard model as an effective field theory. And also he worked and made important contributions on flavor and CP violation. So please, Riccardo, you can start.
Thank you very much. I suppose I have to share the screen, right?
Yes.
Excellent. Is that fine?
Yes, perfect. Thanks.
Very good, very good. So, well, for what has already been said about Weinberg, I am very, very glad to be able to give this talk, in particular on the standard model, because I believe that the standard model in its present form or in some modification of it that may arrive is one of the main achievements ever in the physical description of reality, or at least in an important quadrant of it, constituents and forces. Now, given that fact, it is not a surprise that it has taken a long time to construct it. Nevertheless, since in fact I claim that it's more than 100 years that has taken, I feel important to go through the story, which I plan to do in the way that you see. I will spend some time in describing the making of the standard model, which dates I will defend. I will briefly go through the successes of the standard model, and I will also try to reserve some time for the future of the standard model, because I think that in fact the story is not yet over. Okay, so the making of the standard model. Let me try to reduce my, yes, okay. Now, before entering into the subject, the broad view and the Weinberg legacy, you see the making of the standard model is made, of course, of the content, meaning the construction on effective field theory of the weak and the strong interaction. The strong interaction in parentheses, because in fact this will be more touched by other speakers, in particular over Georgi next to me. And then a full-fledged theory of the weak and the strong interaction. But, you know, equally important is to consider the methodology that was used, also made of two different directions: a phenomenological approach, new concepts to agree with experiments, and the search for mathematical logical consistency. Now, everybody of us knows that Weinberg has been a leading actor in B, in constructing a full-fledged theory of the weak and the strong interaction. But in fact, as it will become clear in my talk, I think he was a leading figure in A as well. And the thing that I want to underline most, a master of equilibrium between 1 and 2. Weinberg, as it has already been said, but even with respect to the approach, has not been a specialist in the best sense of this statement, and I think that this is part of his legacy. All right, so yes, all right, so I begin with really the beginning. You know, the first thing that entered into the game was the realization in experiments mainly in the UK that the beta decay, the beta particles in beta decay had a continuum spectrum. That became clear between 1910 and 1920, generating a big discussion, even putting forward the possibility that there was a crisis of the energy conservation law. As we know, the issue was essentially resolved by the hypothesis put forward by Pauli of his neutron, quote unquote, which was a new particle of speed 1/2. And then what in all respects can be considered as the beginning of an effective theory of the weak interactions is Fermi theory, where, allow me a bit of chauvinism, I quote the title in Italian, Tentativo di una teoria della emissione di raggi beta, which I suppose I don't have to translate for you. And that is the form of the interaction Hamiltonian that Fermi wrote in his very first paper. You recognize everything except perhaps the tau plus, tau minus, which were the raising and lowering operator of isospin as people were using in describing the nuclear interactions. Pretty soon, the more standard notation was introduced that you recognize with the various Lorentz invariant pieces, and again soon recognized to be problematic this interaction Lagrangian in its high energy behavior, because people noticed that, for example, the cross-section for the elastic interaction, the quasi-elastic interaction, was growing like the square of the momentum of the neutrino or of the energy. And in fact, in the 60s, gradually reduced to the current form that we are all familiar with and that you see written down there. Of course, I don't have to recall you that in the 50s, parity violation was discovered as strangeness was discovered, the various strange particles. The leptonic current was clearly written down in the form that we know now, in fact, including also the muon, which I didn't write down. The question was, what about the hadronic piece? Because nobody had a model for the strong interaction. And the key step that was recognized as essential to go forward was to associate the current describing the strong interaction with the symmetry of the strong interaction, because that would have allowed to make consideration to some extent model independent. So in 58, one put forward the conserved vector current, essentially the identification of the vector piece of H mu with the isospin charge current, which made possible to establish beta decay and mu decay universality, because that observation allowed a normalization of the current and of the matrix element, and people were able to realize the universality with beta decay and mu decay. The axial part of the current was more of a problem, but in 1960-62, people introduced the concept of partially conserved axial current, chiral invariance spontaneously broken, pions perhaps as non-Goldstone bosons, and In 62, in fact, one of the first important contribution of Weinberg to this specific area was a paper written with Goldstone and Salam, showing that in general, pretty general terms, that the continuous symmetry and the non-invariant vacuum give massless scalars. At the end of the paper, in fact, the question was raised as to whether this had to be considered as a difficulty, because after all, nobody had seen massless scalars, and we will see how this will go forward. 63, a fundamental step by Cabibbo, who essentially enlarged the SU2 to SU3, the current written alla Cabibbo with the Cabibbo angle you see it written here, right, with the delta S equals 0 and the delta S equal 1. But the most important contribution of Cabibbo was that he understood that by thinking of this current as a piece of SU3, it was possible to make a quantitative comparison of all the strange particle decays, and indeed show that a current like this with the Cabibbo angle was capable to successfully predict all these decays. 64, Gelman enlarged the SU2 cross SU2, if you want, including the observation of Cabibbo, to U3 cross U3, the algebra of currents, as it was called at the time, which one can see it as a product of two U1s and two SU3s broken down to U1 vector cross SU2, SU3 vector. The axial part of this U1 will have to be the issue of the axial part, the fate of the axial part will have to be understood later on. Immediately after, Weinberg started giving a series of contributions, more than one paper, where in his usual style, he translated the algebra of current in a dynamical way of describing their contribution by means of effective chiral Lagrangians applied to pions, baryons, the rho even. As he was saying, current algebra without current algebra. And I suppose that this will be again covered by over Georgi, but this is one of the characteristic way in which Weinberg likes to work, right? Writing down most general Lagrangians consistent with the symmetry and see the general consequences of those Lagrangians. Now, from the phenomenological sort of approach, one passes to the steps towards a full-fledged gauge theory. Now, of course, that proceeded very much in parallel to, excuse me, yes, to the phenomenological approach. Of course, everybody knows the story of U1 electromagnetics, of QED, and also of speculation that took place in that period about SU2 of isospin as a possible gauge theory, often derived from a 5-dimensional theory, interestingly enough. A major step was made in 1954, everybody knows. Young-Mills gauge theory was written down for SU2, and in connection with the phenomenology of the weak interaction, an important step by Schwinger that started rewriting, if you want, the interaction Hamiltonian in a way that is more to which we are more accustomed to, and even trying to discuss the inclusion of a full triplet of vectors that he called Z plus minus, and the neutral and the zero component in a triplet of SU2, trying to identify the zero component with the photon. Yes, now the other steps, very important and also very well known that nevertheless it's worth recalling, is Glashow, that was the first to write down as far as I can tell, the algebra of the generators of SU2 cross U1 as the important generators of gauge symmetry of the electroweak interaction, and even introducing the notion of superposition of the two neutral components here in such a way as to construct the photon. Of course, a major question at that point was where the vector masses were coming from, not to mention the issue of including strangeness and so on and so forth. But this was certainly a major step. In the same year, I think Glashow and Gell-Mann, I think, extended the SU2 of Young-Mills to an arbitrary Lie algebra, started talking of and thinking of a possible unification of all the interaction into a single compact group. The other major steps that we all know about is the Braut and Glert Higgs mechanism with no massless particle anymore, but a massive scalar. And this, of course, is a major step forward that I think Weinberg was perhaps the first to realize how important it was, given the fact that he had suffered the problem of massless particles according to the Goldstone, Salam, Weinberg paper. Okay, so we are at 1967, and the title of the paper that I suppose many of you know and have written, and have read, whose title was A Model of Leptons. Now, I liked to copy this equation from the paper. You see, 4 is the number, the quote of the number of equations in the paper, because you will agree with me if I say that it's not frequent that nowadays you can take an equation from a paper which is 50 or 60 years old and use it, for example, when you give a lecture on the subject. This is the explicit complete Lagrangian for the electroweak interaction, at least for the leptons. Now, which were the important steps that Weinberg realized in that paper? I think the use of spontaneous symmetry breaking, SU2 cross U1 into U1, at least in 3 different directions. First of all, used for the first time in weak interactions, right? As I said, the spontaneous breaking of a symmetry was already discussed in the context of a strong interaction, but this is the time in which this spontaneous symmetry breaking is used in the context of the weak interaction. Of course, in generating vector boson masses, and in the paper, you find the correct lower bounds that, given the knowledge at the time, you could draw on the mass of the W and the mass of the Z. You see, the mass of the W had to be greater than 40 GeV. Of course, these numbers exactly reflect the knowledge of GF at the time. The correct number are perhaps 5 or 10% lower, but essentially correct. The lower mass of the W is obtained by taking G equal E. Nobody knew which was the value of the what will be called the Weinberg angle, or the weak mixing angle. Okay, so you could have taken whatever you wanted for this coupling. So G equal E, G prime going to infinity gives the lower bound on the mass of the W, and G equal G prime equals square root of 2E gives the lower bound on the mass of the Z. I must say that this lower bound were not taken immediately seriously by several people working on the subject. And of course, the other major step, new step, is use of spontaneous symmetry breaking in generating fermion masses, as you see it from here. The Yukawa coupling of the Higgs field with the fermions. In the paper, Weinberg asked, is this model renormalizable? He guesses that it could be the case, but of course, one had to wait the rigorous proof of Toft and Veltman that came a little time after. Now, of course, the other question that remained open during at the end of the paper was how to include hadrons, and the inclusion of hadrons took place in between 70 and 73, with first of all the fundamental step that finally understood how to take care of neutral current, strangest change in neutral current. You see, it's pretty clear that the reason why quarks or hadrons were not included here is because of the fact that one really didn't know how to deal with the problem of neutral current, strange changes in neutral currents, because already several years earlier it was pretty clear that from bounds on this process or from the mass difference K0, K0 bar, to make sense of delta S equal 1 and delta S equal 2, one would have needed a cutoff of the effective Witch interaction pretty low, 2, 3 GeV, significantly lower than the number that I gave you for the masses of the W. And of course, the solution came with the observation of Glashow, Iliopoulos, and Maiani that the current, the Cabibbo current, which is this first piece, had to be completed with the inclusion of charm and the orthogonal combination of Strange and D. Okay. Then, of course, the major steps in the strong sector of the full theory, Gross, Wilczek, Politzer, asymptotic freedom observation, and not less importantly, Gell-Mann, Fritsch, Bardeen, Lloyd-Wheeler, that starts speaking of colored quarks coupled to an octet of gluons. Now, in front of this comes the Weinberg synthesis in a paper that is really worth reading. You know, that's the usual ability of Weinberg of putting everything together in a fully consistent theory, right? He, in a paragraph, in not more than a paragraph, he says, the way to include into the theory that he had already written of SU2 cross U1, the strong interaction had to follow this path. The full group had to be the product of the group for the strong interaction times SU2 cross U1. The fermions had to form non-chiral reps of the strong group in such a way that respecting the strong group, the masses of the fermions could be given. And the third important feature is that scalars are GS neutral, so that the vacuum exploitation value of the scalar leave GS unbroken. And that's, as I think you understand, is the essence of the full story. In the paper, Weinberg asks, again in his own typical style, another crucial question: why the weak interaction do not produce parity and strangeness violation of order alpha, not of order GS, 1 over MW square, of order alpha? And the answer comes by simply writing down the most general dimension 4 up to dimension 4 Lagrangian for the effective strong interaction, where this Z could contain a gamma phi, where this M, which is a matrix, right? We are in flavor space even, there is strangeness included here, okay? So Z is a matrix, 1 plus a matrix times gamma phi in flavor space, including strangeness. and similarly for them. Now, this is the most general Lagrangian you can write down, and Weinberg notices that by psi redefinition, parity and strangeness are accidental symmetries of the strong and electromagnetic interactions, because by psi redefinitions, the gamma 5, you can get rid of the gamma 5. Anomalies are another subject, okay? So you see, I am at the end of the first part. I find useful to show this page, which emphasizes the synthetic character of particle physics. You can write down all of particle physics, provided you know the rules of the game, provided you know what field theory is. You can write down all of particle physics in one page by specifying the symmetry group, by specifying the particle content, how they transforms under the symmetry group, and by stating that all operators included in the Lagrangian have to be dimension less than or equal to 4. Now, of course, this page, which I repeat, I like it very much because it emphasizes the synthetic character of the standard model, does not put the theorists out of business, right? Because the theorists after that have to work a lot to get the consequences. And in fact, there's been very important research that is still going on and is still essential to give exact meaning to this page. But this is the synthetic description of the standard model. And I will come back to this issue of the synthesis of the standard model. Okay, so let me go to the second part. Briefly, right? Because it would take a series of lectures to describe all of the amazing success of the standard model. 1974 now, up to now. Well, of course, the first great discovery that put the standard model in business, the electroweak part of the standard model in business, was the discovery of neutral current. Weinberg, at the end of '71, wrote a paper in which he noticed that given the poor knowledge that he had at the time of the mixing angle, of the weak mixing angle, of the Weinberg angle, whatever you can call it, he put a lower bound and the upper bound on the neutral current versus charge current interaction of the neutrino. In fact, having to find at that time with a upper bound coming from CERN pretty close to this lower bound. So Weinberg was hoping that his theory was right, and he insisted on that. And in fact, at the end of '73, '74, the Gargamel, the bubble chamber operating at CERN, of which you see here the actual bubble chamber that you can see in the CERN. If you enter the CERN site, this is the result that was given for the neutral current to charge current ratio of the neutrino, consistent with this prediction. And in fact, this is an historical plot that you can find in the paper, in which you see the expectation depending on the mixing angle and the consistency of the result with the expectation. Now, of course, the other major success of the standard model is the progressive discoveries of all the expected particles. And here I have photographed the situation in '73 when all the ingredients of the standard model, that's why I indicate '73, right, as the end of the making period, right, were there, including CPV if three families, the observation of Kobayashi and Mascaro, right? Even though, the discussion on the gauge group, the discussion in particular on the origin of CP violation, went on for all the 70s and even later, right? But it's true that all the ingredients that we now think are important in the standard model were known in 1973. And so these were the particles known. All the dates are experimental dates, with the exception of the one in color. You understand why I put to 1905 for the photon. One can discuss the date at which quarks were, quote unquote, theoretically discovered. Of course, quarks were introduced earlier than that, but you know, at the beginning more as theoretical entities and so on and so forth. So roughly speaking, in the 60s, the quarks entered into the game. And here, of course, is the situation in 2012, where, you know, it is interesting to look at the dates. For those of you that don't know them, you see that the 70s have been very, very important and crucial, but you know, even the other particles that have to wait for an explicit discovery. And I let you guess why I have put these stars here. Now, precision in QCD, well, just one slide. This is really remarkable. As you see here, the consistency fixed only by one parameter of all the measurements of the running strong coupling constant. That allows to fix the value of the alpha S2 at MZ with the precision that is better than 1%, as you see it from here. Now, why have I written here Sterman and Weinberg? Because you see, not all, but many of these entries here come from jets. And Sterman and Weinberg dictated the philosophy that then, you know, produced the continuous interaction between theorists and experimentalists, how to define jets in an optical way. But the basic observation is simple. Whenever you define an observable that is infrared free and has a typical momentum that is, say, above, say, 2 GeV, then you can compute it in perturbation theory without making any reference whatsoever to the Parton model or whatever, right? So that was the observation of Weinberg that has been instrumental in constructing this plot. Not less important is the electroweak sector. I suppose that many of you have seen this plot, which puts together all the observables essentially at the Z and the W pole. But it's worth having a look at it. So you see there are 5 entries. The red entries are inputs, right, corresponding to the 5 parameters that are important in the standard model that you all recognize, I suppose. Then there are 3 green observables that are related to charge current, and then several observables related to neutral currents, the Z-pole observables, essentially, right? And the important thing is that each predicted observables in this fit is removed from the fit, right? So this is a real prediction. It's worth, I think, commenting again on the precision of the electroweak fit. This is a plot that many of you may have seen, but it's worth looking at it, right? So you see this blue ellipse, right, is the prediction of the mass of the W and the mass of the top using the electroweak observables that I have described before, compared with the direct measurement. And as you see, the level of consistency. Why this is important? You see, this is important because it is literally true, and I will even come back to this, that the standard model is not capable to predict the mass of the top and the mass of the W. Nevertheless, it is true that there are many observables that are correlated by this parameter, in particular, all of the electroweak fit correlated among themselves through these parameters, which meant that in 1994, before the discovery of the top mass could be essentially predicted, quote unquote, in this way, right? In this way. And in 2012, in fact, already at the end of lab, in the year 2000, the mass of the Higgs could equally be predicted, right? Another way to see the impact of the electroweak interaction is by using these two effective parameters that are capable to catch all the electroweak corrections, the typical gauge corrections, loop gauge corrections, for all the Z-pole observables and the W-pole observables, not only in the standard model, in fact, but for any theory that is flavor symmetric and quark lepton symmetric. And you know, this is what led, I think, the majority of us to think that at the end at lab, that the gauge sector of the standard model had been established. And this, I think, is important, and we'll come back in the following. The last plot that I want to, the slide that I want to show on the test of the standard model is this page, which I call the ultimate precision, which shows the comparison between theory and experiment in the G-2 of the electron, of the anomaly of the electron and the anomaly of the muon. Never mind the level of agreement at the moment. I will even say something later on this. The important thing to notice is that you see the level of comparison is the level of error. The error is the level of 1 part per billion here, and in the muon at the level of 1 part per million. And again, Jakiv and Weinberg in 1974 were the first to compute the one loop weak correction to the G-2 of the muon. Now, I hope you will forgive me if I've included this sketch, but I put it there because it reminded me of the fact that I normally use a page like this when I give a talk to high school students about particle physics, because in fact I think that the collection of this page and the page about the synthetic nature of the standard model, to me, is the most synthetic way of presenting the power of the standard model in all its respects. Yes, here is again the issue of the synthetic nature of the particle physics. Once again, in a way that I am sure you are familiar with. Weinberg would say, as said, the world of physical phenomena reduced to a finite set of fundamental equation principles. That was his way of thinking in terms of reductionism, right? Now, these data, I think, are important. I told you already, you know, the dates are the approximate dates of the experimental tests of the various lines at different levels, right? This is the A sector, and as I told you, the end of lab showed that the basic structure was correct. The X, the test of the X started with lab, essentially, right? And with the incredible importance of the discovery of the X. But I think that is still going on, as I will argue in a second. And of course, the flavor bit, right? With, you know, a construction that started with Cabibbo and so on and so forth. But in terms of tests, it seems to be that the key year is the year 2000, when at least one possible first year is the year 2000, when one first saw direct CP violation in the Keown system. For those of you who remember this notation, the epsilon prime over epsilon first observed to be different from zero, as expected in the standard model, first at CERN and then in the US, and again with the testing that goes on. All right. So how much time do I have, Roberto?
So how much time do you need?
5 minutes.
5 minutes, okay.
Okay. Now, the future of the standard model, is there a difference in the two sectors of the standard model? So I am brief, right? Here there is a little reordering of the gauge sector and the X sector for reasons that I have explained. The gauge coupling of the X cannot be doubted. So this slight reorganization, right? And it is a fact that many of what can be considered problems in of the standard model are in the X sector. The hierarchy problem, you all know what I mean. The cosmological constant problem, which you may say it's not really a problem for the standard model, but in fact, from an effective field theory point of view, they look very much the same, these two problems. And then the flavor problem, which means that the combination of this and this makes that no particle mass is calculable in the sense that I said, with the qualification that I said, there is no particle mass except for the photon and the gluon that is calculable in the standard model, which makes me think that this is a legitimate question. Can we tell for sure that we know the true nature of electroweak symmetry breaking? Of course, I agree, this is a pretty conservative question, yes, but in science to be conservative is meaningful, and maybe this is a question put forward by an old man, as I am, but I think that it makes sense. Also because, based on this comparison, here you see the calculation of the measurement of the various coupling of the X, typical precision 5-20% against the precision in the electroweak test at the level of 1 per mil, okay? Which makes me think that this and the previous page make it that a X factory is due to what? To the cultural evolution of mankind. Best, of course, if it's on the way to an ion energy collider. This seems to me one important step that should be taken in the future if we want to really understand the true structure of the standard model. And we know the reasons, would take a seminar. Even this page, you probably know, right? The problem of question for the standard model, the issue of neutrality of hydrogen, right? That cries for some sort of unification. And of course, here I underline again the contribution of Weinberg, who together with Georgi, Ellen Quinn, first showed how the evolution of the coupling constant could lead to unification. Of course, there are phenomena which are unaccounted for, we know. There is the issue of why there is apparently one single operator in the standard model, according to the rule that I have given before, that needs to be, that doesn't seem to be there. You know the story of actions, you know the contribution of Weinberg to that. Why only D less than or equal to 4 operators? Neutrino masses, proton forever. Weinberg made the full list of the operator in 1979, making a lot of important observations. And then, of course, lack of calculability, as I said already. Now, there are current anomalies in the test of the standard model, and this is a partial list, which, however, is not badly chosen, I think. Except for the muon G-2, they all refer to semi-leptonic BDKs, charge and neutral. And you see that there is a consistent displacement of all the neutral current observables in semi-leptonic BDKs with respect to the prediction. As it is the case, although with a fewer number of observables in the case of the charge current. And we have all order of the muon G-2. Now, to comment on this is not really part of the talk, but there are general lessons to me, which are the following. In many cases, the theoretical prediction is definitely more precise than the experimental precision, which means that a precision program has to be followed in the coming years in flavor as in flavorless physics, right? This, I think, is a very important step for the next decade, say. If confirmed, and this is an important qualification in my view, but not the subject of this talk, the coherence of BDK anomalies are suggestive of some approximate flavor symmetry that plays a role in understanding what's going on here. And also, independently, to me, the G-2 of the muon, in case it is confirmed, can be easily interpreted as a first sign of supersymmetry. Of course, if they are roses, they will flourish. Now, where is the scale of flavor? Of course, you see, if flavor is confined to high energy, then certainly all of these anomalies will have to go away. However, it makes a lot of sense to think that new physics in the multi-TV is hidden by a suitable approximate flavor symmetry. All right, let me finish by let me make Weinberg speak. Now, Weinberg was not only a great physicist, as it has been said, but it was also a great intellectual, which meant that he regularly published in the New York Review of Books, among many other interventions, public interventions, a series of articles, all very interesting to read. Here, November 7, 2012, the same year of the discovery of the Higgs, Weinberg writes an article whose title is Physics, What We Do and Don't Know. Now, I copy one paragraph towards the end. He says, even so, the standard model is clearly not the final theory. Its equation involve a score of numbers, like the masses of quarks, that have to be taken from experiment without our understanding why they are what they are. And you can go on. A few paragraphs later, he says, inflation is naturally chaotic, bubble form in the expanding universe, perhaps each with different values for what we usually call the constant of natures. Then he says, if this is true, then the hope of finding a rational explanation for the precise value of quark masses and other constants of the standard model that we observe in our Big Bang is doomed. We would have to content ourselves with a crude anthropic explanation of some aspect of the universe we see. And you can keep reading. You see, there seems to be a contradiction between these two statements, right? Isn't that the normal reaction? I don't think there isn't. In fact, look at the title of the paper, What We Do and Don't Know. The search goes on. Thank you very much. Sorry for having kept you a little bit too long, perhaps.
Thank you very much, Riccardo, for the great talk. Okay, so I think we can have now specific questions on your talk, if there is any, so people can raise their hands. I would really limit questions now to those on specific aspects of your talk. Otherwise, more general questions or comments can be asked at the end.
We have one in the chat.
Let me see. I have somehow lost the page. Let me.
Yeah, so I can read it for you if you want.
Thanks.
So Jay Harnard is asking, can the standard model be used to compute the proton-proton scattering amplitude? And can the standard model provide the range of the strong interactions? Strong interactions.
To compute the
proton scattering
proton cross section
and provide the range of the strong interactions.
Yeah, if you put together enough experimental information with the essence of the standard model, you can, sure. Why not? You have to put together enough experimental information in a range in which the standard model suffers from the fact that the strong interaction part of it in the low Q momenta is not straightforward to analyze, but you know, very much in the same way. But you can certainly end up with a prediction for proton-proton collision and the range of the strong interaction. Yes, I have shown you. I don't know if you see my screen. Do you see my screen again?
We do.
Yes.
Yeah, we do.
Yes.
So you may remember this page, right? Or this page. This page tells you that, you know, at lambda equal, what, 200 MeV, the coupling constant explodes and you have to deal with the problem. Yes.
Very much. It choose a few areas that I'm most curious about and that bear the imprint of Steve's unique style. There are few physics papers that I read for pleasure every few years. One of these is Steve. I was an undergraduate, probably while I was taking Schwinger's course on source theory. At this point, what Steve means by a phenomenological Lagrangian is one in which the interaction terms are used only in first order. Having only derivative interactions is crucial because it means that in the chiral limit with massless pions, as the pion energy goes to zero, the amplitude goes to zero unless the derivative is compensated by a pole on an external line. One of the clumsinesses that Weinberg refers to here is the starting point. He starts from the old linear sigma model of Gell-Mann and Levy, which has the right symmetry, but it is otherwise not particularly well motivated. And Steve had to compensate by putting in the physical normalization of the axial vector current by hand. The other clumsiness is that the symmetry structure is only approximately right. But at least to first order in the pion fields, the pion couplings vanish except for derivative terms, which was the crucial thing. Now here's the fun part. Again, the bold is mine. I don't know whether Schwinger already knew about the clever mathematical trick of induced representations that he suggested that Weinberg use, or whether he invented it independently. But the idea is this. To build an induced representation of the chiral symmetry, you construct a chiral transformation on the matter fields as an ordinary isospin transformation by an angle that depends on the pion fields. And then you find a nonlinear transformation of the pion fields that reproduces the full chiral algebra. The chiral transformation is said to be induced from the isospin transformation by the nonlinear transformation of the pion fields. And this can be applied to any isospin representation. So the isospin transformation is then local, depending on position, because it depends on the pion fields, which depend on position. But because the pion fields appear only in the angles of the isospin transformation, they disappear completely to all orders from any isospin invariant term without derivatives. The Lagrangian depends on the isospin of the matter fields without any assumptions about what SU2 cross SU2 representation they are part of. Physically, this means that it's simply meaningless to ask about the chiral transformation properties of the matter fields themselves. And now to all orders, the pion couplings all involve derivatives or explicit symmetry breaking terms. One of the many things that I love about Weinberg's paper is the deft way that he handles Schwinger's source theory, paying homage to Schwinger without noting that Schwinger was not really doing anything interesting at this time. And while it's certainly true that many physicists had pieces of the puzzle that Weinberg completed in this paper, Weinberg deserves credit for expressing the idea so clearly and in such generality. As Ricardo mentioned, generality is Steve's specialty. But why is this the right thing to do? The paper contains a very clear statement of one of the central dogmas of effective field theory, that field theory by itself has no content beyond Lorentz invariance and quantum mechanics. Perhaps Nima will amend this for us later today. But the key point here is that the new idea is that the momentum expansion can explain in what sense non-renormalizable quantum field theories make sense. The momentum expansion is an expansion in powers of the energy, and in this case, the symmetry breaking parameters, and it replaces and systematizes the notion of smoothness of amplitudes that was used in the old current algebra calculations. This is what is referred to as chiral perturbation theory. But more generally, Steve realized that the momentum expansion is the key to doing reliable calculations in renormalizable theories, including quantum loops. Even though there are an infinite number of parameters and an infinite number of counterterms required, only a finite number of them are required to calculate to a specific precision at a specific energy. And when coupled with the momentum expansion, Weinberg's Folk theorem about quantum field theory becomes a powerful tool that incorporates information beyond traditional perturbation theory. So the first thing I want to talk about is, where did this paper come from? It's so wonderful. I want to spend a good part of my talk discussing the history that led up to this beautiful synthesis. One possible source for this history is Weinberg himself. This is one of many papers written about that history. It's the opening talk at a conference celebrating the 30th anniversary of his Schwinger-Festschrift paper. And there are many similar talks. Here is Weinberg's summary of the progression. The starting point, of course, was Nambu, spontaneously broken symmetry, and so-called partially conserved axial currents. And Steve describes the progression from Nambu and PCAC through the early work on current algebra to his nonlinear chiral Lagrangian that allows current algebra calculations to be done more easily. And then he suggests that he lost interest until the late 70s, when he was inspired by Wilson's work on scaling in condensed matter physics and his attempts to justify quantum field theory to his students. It's a good story, and he writes beautifully as always, but it didn't convince me. I think there's some very important influences that are left out, and I wanted to dig into the history a bit, and this talk gave me a good excuse to do that. Nambu's PCAC did not catch on immediately. You can see that in the citations to Nambu's paper as a function of year. Initially, physicists just struggled to understand the physics of the Goldstone theorem, the connection between spontaneously broken continuous symmetries and massless particles in relativistic theories. Steve's paper with Goldstone and Salam, which Ricardo mentioned, was one of many examples, though of course it was a particularly clear and general treatment. But after the success of Gell-Mann-Neyman's eightfold way and the Cabibbo angle, the game heated up, and there was explicit discussion of the chiral SU2 cross SU2 and SU3 cross SU3 symmetries, and many applications that depended on the commutator structure. Steve, as usual, considered a very general situation and worked out the current algebra of an arbitrary number of pions. Even Steve thought that this was complicated. This is a typical page from this paper. But one beautiful thing that came out of this complicated mess was Steve's calculation of low energy pi-pi scattering. This calculation gets to the heart of the non-abelian Goldstone theorem, and it can be understood very simply classically. A Goldstone boson wave packet is a local twist in the vacuum. And at low energies, the interactions go to zero because the packets look very much like the vacuum everywhere, but like slightly different vacua in different places. So, for example, two pi0 wave packets don't scatter from one another because all of the twists of the vacuum are about the same isospin axis, and they commute with one another. So the passing pions can twist and untwist the vacuum, leaving nothing behind. But a pi0 and a pi plus correspond to twists in different isospin directions, and the twists don't commute. So now the system is complicated in the overlap region, where one pion twists the vacuum and the other twists it in a different direction before the first one can untwist it. This leaves behind a little region of space with the vacuum twisted in the direction of the commutator, and this spreads to become the scattered fields. And that's the classical Goldstone boson physics behind Steve's pi-pi scattering calculation. The next thing that happened was that, according to Steve, he was sitting in a cafe in Harvard Square when he realized that he could find a Lagrangian that, when used in lowest order, would reproduce the effects of current algebra in a much simpler way. This was the clumsy approach that I discussed at the beginning of the talk. So finally, in 1967, Steve follows Schwinger's suggestion and constructs a fully invariant nonlinear theory using the mathematical technique of induced representations. So then there's a break. He says that only after a break of nearly 10 years to construct the standard model was he motivated by condensed matter physics and by his teaching to think again about the problem, and then finally tamed the infinite number of parameters and realized that non-renormalizable theories are perfectly renormalizable, and the momentum expansion allows one to calculate with them. At that point, he replaces the old-fashioned constraints of renormalizability by constraints on the sizes of non-renormalizable terms in the effective field theory. And this modern picture of effective field theory is born. So Steve's account makes a really good story, but I think it leaves out many important developments that almost certainly influenced his thinking, and I want to show you why I think so. These include maths-independent renormalization schemes, GUTS, effective theories of the weak interactions, heavy quarks, and perhaps most importantly, the U1 problem. So it's certainly true that Steve was doing other things besides thinking about pions in this period, but not immediately. This was a depressing time for quantum field theory. Weinberg's model of leptons paper did not make a big splash when it first appeared. I was just a baby at the time, but I remember seeing it when it arrived in my mailbox, and like most everyone else, including, I think, Steve himself, I ignored it because it didn't look renormalizable to me, and I didn't really know how to make precise sense of it. This shows up spectacularly in the plot of the citations to Steve's paper by year. There was equally little excitement when Glasgow and Iliopoulos and Miami figured out why a charm quark had to exist to explain the absence of neutral current effects that change flavor. I must say the statement of the Jim mechanism is very simple. If there are 4 quarks and they come in 2 complete families, each with identical weak charges, the strong interactions have an approximate SU4 flavor symmetry, and flavor changing neutral current effects are proportional to the SU4 symmetry breaking and can be adequately suppressed if the symmetry breaking is small. I think this is one of the most brilliant and annoying developments ever in particle theory. The reason that I think it's so annoying is that it implies that we have absolutely no idea what flavor really is. And as Ricardo mentioned, in the standard model, that turns out to be true. At any rate, these frustrations ended spectacularly in 1971 after 't Hooft figured out how to make sense of spontaneously broken non-abelian gauge theories in general, and Weinberg's model of leptons in particular. This obviously is the reason for the jump in citations to the Weinberg and Jim papers, and also to the resurgence of quantum field theory in general. 't Hooft's work opened up a new region in the map of quantum field theories, and some of us started exploring it by building models, both to see what was possible in this new class of renormalizable models and to try to find the right model. So I will discuss one completely crazy model building exercise in detail. James Byrkane, BJ, did something crazy that was both wrong and important. He came up with a numerological relation for the ratio of the muon mass to the electron mass. And he argued, and as far as I know, this is not published, that the relation was correct up to just at the level that one would expect if there were radiative corrections. It's right up to order alpha squared. Now, in hindsight, this seems completely ridiculous. But you have to remember that at this time in 1972, there was no tau lepton, and we weren't quite sure what to think about quarks. For many quantum field theorists, quarks were still a shorthand for symmetry properties of the still mysterious strong interactions. That situation would change like dreams over the next couple of years. But in early 1972, it seemed entirely reasonable to construct models in which mu over me is calculable. At this time, Steve Weinberg was still at MIT, and he got interested in the same problem. So we had a little contest between Shelley and me at one end of Cambridge and Steve at the other to see who could compute the muon electron mass ratio. Although I think Shelley and I came closer to the goal, Steve made theoretical contributions that were much more important. He wrote a paper which described a model of leptons, his second and much less well known than the first. It was based on SU3 cross SU3. And he reasoned that in this model, after symmetry breaking, there would exist Feynman graphs like the one shown here that might give BJ's formula. This is a brilliant wrong paper. Steve's model doesn't give anything like BJ's formula. He missed a counter term, and the electron mass is actually infinite. Shelley and I showed this and understood how to fix it by adding another SU3, but the solution was boring because instead of the square root of 2 in BJ's formula, we got a complicated ratio of heavy vector boson masses. And if we knew all the masses, we'd have a relation, but that didn't seem like much. The really interesting thing about Steve's model is that it is a kind of proto-gut. The gut-like properties can be seen in a simpler model with only one SU3, with both triplets transforming as 3s. The point is that unlike SU2 cross U1, but like all gut models, this SU3 model has gauge interactions that we haven't seen. In this case, the right-handed weak interactions involving the top and the bottom components of the triplets. and also weird doubly charged currents involving the bottom two. To get rid of them, Steve invoked what he called super strong symmetry breaking. He added an octet scalar field with a vacuum expectation value in the lambda 8 direction and gave it a big vacuum expectation value. That breaks the SU3 gauge group down to SU2 cross U1, as we all know from Bellman's SU3. But in this case, it's used in a completely different way to give a large mass to all of the unwanted gauge bosons in this model. So these super heavy gauge bosons were constrained more by their virtual effects than by direct bounds on production. At this point, Steve was certainly not thinking about what are now called gut masses. In those days, a few or 10 times the W mass would have been plenty to suppress the unwanted interactions to an acceptable level. Needless to say, at the time, it was a pretty radical concept because we all still thought of the W and the Z as extremely heavy. To invent things that were heavier still was a bizarre act of genius. Because there's only one coupling constant in the model, because there's only one coupling constant in the model, the weak mixing angle is also predicted. And it's predicted to be a quarter, which at the time didn't seem very good, but now seems great. But of course, he was ignoring renormalization effects because nobody was thinking about at this time, because nobody was thinking about really large mass ratios. It's the fraction in this case, ignoring renormalization. The weak mixing angle is just the fraction of the total charge in the group invariant sense that comes from the SU2 gauge coupling right up here. Steve, as he was wont to do, generalized the question. He generalized the issue of BJ's relation into something much more interesting by expressing what we'd done in a symmetry language. What we found was a model in which the most general renormalizable Lagrangian had no mass term for the electron, so that the kinetic energy terms had a chiral symmetry. But the full Lagrangian did not have a chiral symmetry for the electron field, so that the electron gets a mass due to radiative corrections, and the mass is finite and calculable because there's no counter term to absorb the infinite contribution. Steve recognized that this sort of thing happens frequently in non-abelian gauge theories and suggested that it might be an explanation for some of the approximate symmetries we see in the world. The issue may require a little explanation. Symmetry, both gauge and global, played an important role in renormalizability from the very beginning. But nowadays, exact global internal symmetries have a bad name in quantum field theory, and we suspect that there may not be any at all. But approximate global symmetries are an obvious and important feature of nature. We knew how to use them by simply assuming that the Lagrangian of the world has a symmetry conserving part that is somehow large and a symmetry breaking part that is somehow small. But this might seem a little artificial if the symmetry breaking small part was governed by a parameter that was in some sense infinite and required renormalization. Steve realized that there were examples of QFTs in which the symmetry breaking term, like our chiral symmetry breaking electron mass, is finite and calculable in terms of other parameters because it's not present in the most general renormalizable theory, and therefore no counter term exists to absorb an infinity. I think that Steve invented the name accidental symmetry for this situation, and I'm almost certain that I heard the name from him. It appears in a footnote in his paper on the subject. In our solution to BJ's challenge, the chiral symmetry of the electron kinetic energy term is an accidental symmetry. It's an automatic consequence of the constraint of renormalizability. But the problem with these models was that they could not accommodate fractionally charged quarks. And evidence for these from deep inelastic scattering had been piling up, and by this time it was getting pretty convincing. So after years of experimental results, which were very interesting but not easily theoretically interpretable, the deep inelastic scattering from SLAC was beginning to make sense and beginning to look like really interesting, though still confusing, quantum field theory. Another interesting thing that happened in this time was that Bouchiat, Iliopoulos, and Mayer, and Gross and Jakif reminded us that the existence of triangle anomalies put interesting constraints on these models. And Bim noticed that 3 colors of quarks was the right number to cancel anomalies in the electroweak model. So this fit very nicely with the original suggestion of 3 colors from baryon spectroscopy. So after the discovery of weak neutral currents, the basic structure of the electroweak interactions was pretty clear, but the nature of the strong force and the full significance of color was still not obvious. Of course, a big part of the push for quarks came from dimensional transmutation and asymptotic freedom. Dimensional transmutation was described by Sidney Coleman and Eric Weinberg in another of my favorite physics papers, Radiative Corrections as the Origin of Spontaneous Symmetry Breaking. The subject is a version of Weinberg's model that I think is pretty uninteresting, but the paper is a how-to-do-it manual of useful techniques in quantum field theory, the renormalization group, the loop expansion, the effective potential, and much more, written in Coleman's best pedagogical style. Almost in passing, they show how renormalization can convert a dimensionless coupling constant into a dimensional energy scale, characterizing the interaction. I didn't realize at first how important this was going to be. The history of asymptotic freedom is complicated, and I'm not going to get into it except to say that I spent a lot of my time during and after 1973 trying to do useful physics with it. At first, though, we were still assuming that we had to break the color symmetry and not yet recognizing the full power of dimensional transmutation. The recognition that color symmetry could be unbroken and the quarks confined developed gradually to many people over that year. And I first heard it from Steve in this paper. This indeed shows that Steve was thinking hard about current algebra even during the exciting time when we were building the standard model. And the paper also contains the speculations about what we now call quark confinement. And that idea was very important to me personally because it got me and Shelley thinking about unifying SU3 along with SU2 cross U1. So I've told the story of the evening that I found SO10 and SU5 guts elsewhere, so I'll skim over it almost instantaneously. But I started by thinking about the Pati-Salam SU2 cross SU2 cross SU4 model. This is a beautiful model, or almost a beautiful model. They discovered something very beautiful and then ruined it. They were probably the first to write down a model with charge quantization that could incorporate fractionally charged quarks. And in fact, Braun-Peiss tells me that, ironically, they may have been the first people to write down the full gauge structure of the standard model, which is contained within their model. And I say that this is ironic because having written down the beautiful gauge structure that could explain fractionally charged quarks, they proceeded to do something absolutely gross to it. They spontaneously broke the color SU3 and the electroweak down U1 down to a subgroup that left the quarks with integral unnumbered charges. When we finally understood that it might not be necessary to break color SU3 symmetry at all, and that the massless gluons might be confined, it was easy to turn this into something more interesting. And basically, the first day that Shelley and I started thinking about guts, we thought about it during the day and didn't get anywhere. And then I went home and worked out the structure of the SO10 and SU5 theories in one evening. The idea was you start with Pati Salam and get rid of the ugly symmetry breaking. And then you can immediately realize that the SU4 cross SU2 cross SU2 has an algebra that's equivalent to the algebra of rotation groups, SO6 cross SO4. So any idiot would think of combining these into SO10. And the interesting part was that I didn't have to think about what representation to look at. The spinor representation was the unique choice. So the group theory put the quarks and the leptons and the antiquarks all together for me into a single representation. That was something that Shelley and I had been unwilling to do, and that's why we weren't getting anywhere. In the Pati Salam model, getting rid of the right-handed neutrino broke the symmetry down to SU3 cross SU2 cross U1, and I asked myself what subgroup of SO10 remained after I got rid of the right-handed neutrino. And eventually I saw that it had to be SU5, and then I could do all of the familiar calculations. And get the weak mixing angle and everything else. I now looked at the extra gauge bosons. That had been, I'd avoided that in SO10 because it was complicated, but in SU5 it was easy. And I drew the relevant diagram, which was clear that it would produce proton decay, and I was devastated. I went to bed. I knew the proton was stable. But Shelley, when I told him about it the next morning, was more excited about proton decay than anything else. And he was right, of course. We went up to the library and looked up the bounds and found that our super heavy gauge boson using Steve Weinberg's mechanism of super strong symmetry breaking had to be greater than 10 to the 14th GeV. We wrote the paper and went on to other things. I stupidly didn't include SO10 in a footnote, which gave Fritsch and Minkowski the opportunity to find it independently later on. In the next few years, I wrote only 2 papers on guts. One was a conference report about SO10, but the interesting paper for this conference was the Georgi Quinn Weinberg paper, in which we computed the renormalizations of the couplings in guts and predicted the proton lifetime. The problem that GQW solved was that the then conventional picture of mass dependent physical renormalization was very inconvenient in a theory like SU5 with very different physics at very different scales. In principle, a mass dependent physical renormalization should allow you to evolve couplings from the gut scales to low energies and see the coupling splitting. But in practice, it was a hideous mess. So the key idea was that below the scale of the breaking of the gut symmetry, the leading logarithmic renormalization effects were just what we could calculate in an SU3 cross SU2 cross U1 model, and the unification could be put in simply as a boundary condition at the gut scale. We justified this by appealing to the Appelquist-Carrizone theorem and using different mass-independent renormalization schemes in different energy regions. This was a modern effective field theory calculation, although we did not describe it that way at the time. The couplings in the different regions evolved differently and were connected by matching at the symmetry breaking scale. This was a departure from the conventional view of renormalization as relating directly to physically measurable properties. It fit nicely with the 't-Hooft-Veltman scheme of dimensional regularization and minimal subtraction, but only if we supplemented it by an effective field theory idea of different theories in different regions. And that idea is, in fact, absolutely required to make minimal subtraction useful in any theory with multiple energy scales. I don't have much use for anthropic arguments, but I am enormously grateful to have been born into a universe in which God has chosen the parameters to illustrate almost every possible interesting theoretical idea relative to the standard model. And heavy quarks are a great example of that. Because I'm running out of time, I'll skip over the details here, but basically the parton model was really confusing initially, because some parts worked great for the deep inelastic electron scattering, but it failed badly for E plus E minus. And when many of us were convinced because we tried everything else, that charm had to exist, and that the problem with E plus E minus, the E plus E minus parton model, was that charm was being produced. Now, as the J psi was being discovered at SLAC, Bert Richter was actually a Loeb lecturer at Harvard, giving lectures on his theory that the rising R that they saw at SLAC was due to the fact that the electron was a hadron some fraction of the time. And at a lunch for Bert in the department, David Politzer and Tom Appelquist suggested that they look for narrow peaks in the data. And of course, Bert ignored that. The announcement of the J psi occurred a bit shortly thereafter. It was actually surprising how long it took to actually see charm, but eventually, it's useful to remember that half of the explanations of the J psi in the famous PRL after the discovery were silly, even things by very famous people like Schwinger. But it ended happily. Charm was eventually discovered exactly where we said it should be. R in E plus E minus was starting to look exactly like Appelquist and Politzer said it should, except, of course, in the meantime, God had thrown us an extra heavy lepton. And in the space of less than a decade, we'd gone from confusion to confidence. And quantum field theory was ascendant. But the interesting point for Weinberg was that we had several new energy scales above a GeV. Certainly the charm mass and the W and Z mass, and plausibly a gut scale. And we could no longer ignore the effects of running between these scales. It was becoming obvious that some version of effective field theory was the way to deal with this. And the question was, how does it work in detail? All of this was in the air, and I just don't believe it did not have an effect on Steve's thinking. As far as I know, one of the first people to really figure out the details was my office mate in the late 70s, Ed Witten. And while his calculations are not exactly described in the same language that Steve uses, all of the pieces are there. The last piece I wanted to mention is the U1 problem. Classically, the symmetry of three massless quarks has an extra chiral U1, and it is a disaster. Nothing would work. It was when the quarks were not real and were just you just used them to abstract symmetry properties, you could ignore that problem. But that was no longer true, as now that the reality of the quarks had become more or less established. In fact, there's a smoking gun here that shows that Steve was thinking about these issues in 1975 during this period where he says he wasn't really thinking about it. This is a delightful little paper It shows that changing the decay constant of the U1 current can't help very much. So if anyone was not confused already, this paper would certainly have gotten their attention. But in fact, most people were already confused. And one reason I think that people weren't trying harder to sharpen the tool of chiral perturbation theory was that it seemed it didn't work and that something important was missing. And again, 't Hooft came to the rescue. After 't Hooft's paper, there was no reason not to dive back into chiral perturbation theory and really make sense of it. And that's what Steve did. I want to say just a few words in the few minutes I have left about after phenomenological Lagrangians. But my main message is that everybody should go back and read this paper. It's just so beautiful. So the legacy of phenomenological Lagrangians goes in many different directions. And many of the most solid and convincing of these go through Baird. I still remember a seminar by Harry Leutwiler over 30 years ago talking about the program that he and his colleagues had established to push the phenomenological Lagrangian program further. Harry described their superb work testing the theory, and then he compared chiral effective field theory to an appliance manufacturer and with some revolutionary patents. And he said in his talk, he said something like, if you like the refrigerator I just showed you, I have a washing machine and a microwave to sell you. He was referring to the fact that they could use the same technology, not just in particle scattering, but in lattice QCD, in QCD at finite temperature and pressure, in QCD in a finite box, etc., etc. It's a beautiful collection of applications. Finally, citations can be an unreliable tool but because I don't have time or the expertise to discuss all of the many descendants of Steve's work on effective field theory, I've just listed some research papers, not review papers, just new research that refers to Steve's phenomenological Lagrangians paper, and which themselves have generated more than 500 citations. Just the titles here show a remarkable story of how far and how widely Steve's ideas have spread. And this doesn't include many influential works that involve effective field theory but don't involve the chiral symmetry, but they still have their roots in Steve's ideas. So it's an absolutely remarkable legacy. And he was a remarkable physicist. And thank you for encouraging me to look into this history a little bit.
Thank you. Thank you very much, Howard, for your very nice talk. So there is time for a few questions on your talk. If there is anybody, he or she can raise a hand. Okay, I don't see any question. I don't see any hand. So I thank you again. And at this point, we have a break, a very short break, so 20 minutes. Everybody can rest, and then we reconvene at 5:10 p.m. Central European time. So in 20 minutes from now. Thank you.